All right, so we've already talked about the question number one. We talked about how these compounds break down into ions. And so now today, did we do number two? Okay. All right. I think we actually started talking about it, but I don't think we actually worked it. Yeah, that's what it was. So this is kind of one of the questions I told you is where they're going to get you, they're going to cheat you, they're going to do you dirty because they've given you the units and things that are aggravating to absolutely deal with. And what are the two units they've given you that are aggravating? Very good, milligrams and milliliters, because we know that we can't do either one of those things. We can't use either one of them. So we've got to figure out exactly how we're going to be able to convert them to the units we need. So, number two, we've already started this, so we need to calculate the molarity, which I said, in its basic form is what? Moles over liters. One of these is easy to get. What's the easy one? Liters, okay? Which is wow, my bad. Are there other units of mole? There are millimoles, but that is a profane word. We do not talk about millimoles. It is a cuss word. Do not use the term. Because I hate it. Yeah, I hate it. Millimole. No, it's just 1 times 10 to the negative third moles is the same thing as a millimole. Well, no, I mean, milli is 1,000th of. No. See, this is why I told you, millimoles are profane words. We don't deal with millimoles. Okay? Instead of writing 1,000 meters, you write, or 0.001 meters, you can write 1 millimeter, right? Instead of writing something times 10 to the negative third moles, you can write blah blah millimoles. Yep. All right, so the easy one is to convert, and I'm tired of hitting the wrong button. So I've got 0.433 liters, and the difficult one is going to get our moles. We've already established that this milligrams is aggravating. So how many grams would that be? What would we have to do to the decimal? Move it how many places which way? 3 to the left. So I've got 0.1846 grams of potassium dichromate. Now, is that potassium dichromate something we can work with? The unit given. Unit given. No, it is not something we can work with. So what do we have to do with it? Convert it to moles. So 0.1846 grams. Somebody let him in, please. K2Cr2O7 grams. The troublemaker in pink. Okay. So 1. What will go in the grams location? Okay. The molar mass is, very good, Sarah, 294.2 grams. Now, I'm just going to write the word equal, and where is that number really going to go? That's going to give me what? Moles. But I don't want to have to write it twice, so I'm just going to write it above the liters. Say it again. Yes, it is. 294.2. I promise that's right. Does anybody else dispute that? Calculate it again. That's all I can tell you to do. Okay? But I know that's right. So 6.27 times 10 to the negative fourth moles. Okay? So that is, and again, that is your number of moles. And so this would give me, hopefully all of you already have this answer. What was the concentration? Okay, 0.00145. I have two other ways I'm going to write this. How many of you did not write it in that way? How did you write it, James? Very good. And I'm even going to, Charles, I'm even going to throw you a curveball because you've never seen this one either. I'm going to go real crazy with it. .45 millimolarity. Ooh. is profanity in chemistry. No, it's really not. You really can do that. I mean, that is legit. That is real. Please don't. No, please don't. I'm being funny. Don't do it, Nick. Nick, I'll take points away if you do it. How's that sound? They're going to laugh at you and say, this guy's an idiot. No, they really wouldn't. They'd actually probably say, wow, I'm impressed. He knows his metric conversions. But these are your three. I'm telling you, without any questions, that these are the only two optional choices that I would go with. You could, but Jacob, let me throw this at you. Whenever you're given an answer, and the question is what is the concentration and what is the molarity, I would prefer you to use the M versus the brackets. The brackets are mainly intended for mathematical applications, not result application. You use it within, not the result. Does that make sense? Okay. Like I said, it's not wrong, but it's just not proper. It's not appropriate. Yep. Okay? All right, so that is that problem. Everybody get there. So let's go down to number 3. I like this problem because you've got to use your brain. You've got to use some words. Okay? Describe. As soon as you use this, and I'm telling you every year, this is the problem that students have. You can't use your verbiage. You can't use words to explain what you're supposed to do. And this is the skill that I've got to get better because you don't have it yet. Describe how you would prepare, which means give instructions, a 7 liters of a 0.75 molar potassium dichromate from solid K2CrO4. Now, as soon as you see this word right here, what unit should pop into your head? Grams. You know, somehow, some way, you're going to have to use grams because it says solid. If I changed all of that to 7 liters of a certain concentration of sweet tea, it'd be a lot easier in your head, right? Because you know all of those things. But because it says this, you instantly freak out. You instantly have a change of heart because you're like, oh my gosh, this is chemistry and I don't ever want to do it. But before you can describe, you've got to get grams. How do I get grams from what has been given to us? Thank you. So they've actually been generous in this problem. There's not a whole lot of converting you have to do before you can start your work. And I'm just going to throw this at you. Molarity is moles over liters, right? So I've got to get grams. What's the only way I can get 2 grams from molarity and volume? I've got to get moles first, right? Well, moles is equal to what? Molarity times liters. You would be shocked at how many times that I continue to have to say that throughout the year. Moles is molarity times volume, okay? Or specifically molarity times liters. So they've actually been courteous in what they've given us. They've given us 0.750. Now, Jacob, this is when it will be appropriate and proper to use your brackets. Okay? Because it's the mathematical application. And so then we would use parentheses to do 7.00 liters. Now, just let me throw this at you as a side note. You'll notice that sometimes as I'm doing calculations on the board, I don't always continue with the significant figures. But on May 2nd, when you're actually down there writing the answers, should you write down the numbers as they are explicitly written? Please do. Take the extra second and a half that it takes to do .00. Don't just write it. Sometimes I get lazy just for speed. I'll leave all that stuff off. Like I'll leave that 0 off. But on that day, make sure you use continuity in how they word the problems as well. So this is going to give us a specific concentration. Does anybody have that concentration already? What is it? Okay. No, why did I say concentration? I meant number of moles. Yes. So 5.25 moles. Okay. 5.25 moles. So then we've got to start and we've got to add we've got to get it to grams. Okay. The good news is this the same compound from earlier? Nope. Yeah, this is chromate, not dichromate. So that is aggravating. So in 1 mole, how many grams? Nope. Nope. 194.2. Anybody dispute that? Anybody agree with that? The molar mass is 194.2. Okay, so what it should be. It's what it should be. Okay. Now, how many grams would then this give us? Okay, there's two ways you can answer this. What did you say, 1 point or 1 comma? 1. Now, is that really the best way to write it? No, there's another unit we can use, and what would that unit be? Shut up. Oh, let me ask you this. How many significant figures should you use? 3. So really, I need 1.02 kilograms of K2CR04. They would. Like I said, obviously I would leave it at, I would do 1020 from the initial standpoint, but they would accept 1019. Yeah, sorry, let's make this more efficient. This is a comma, like thousands, and this is a decimal, like 1 point. Okay? But they're still the exact same numbers. Would you receive credit for both of these numbers? Absolutely. If this were a free response question and this were the question, would you receive points for this work? Honestly, I think you would have possibly already received 2 points. 1 for sure, 2 potentially. You would have received the point for the moles and received the point for the grams, but they may have just said, no, just grams. Okay. Then, are you done with this question? No, because they asked you. They didn't even ask you about the mass. They don't even care. But you had to solve for it to be able to describe it. Yes, sir. All right, Nick. So I'm going to go the Nick way, the lazy way. You just described and you did all that in your calculator. You would have. Then you use. So what did you not show up here? You just wrote that number down. So you showed. Did you show that part? Oh, you explained your math. You didn't do the math. Okay. I agree. Well, I'm coaching you. Because if you were to see the key from College Board of how this problem was done, the first thing you would have seen was every bit of this. They would show the math. Okay. What I was getting at was so many people eliminate all the math and just start with this number. Yeah. Yeah. So basically what you said is you would determine the number of moles from the concentration. Yeah, just read it to me. Yep. So then you wrote all of those words when. How much less time would it have taken to write this? You don't have to describe the math. Really, what they're looking for is just this. Because, let me tell you why. Because specifically, what does it say? From solid. So really, they only need the description to include the solid. The mathematics doesn't have to be written. It just has to be shown. Because that took you a lot longer than to do what I did, right? I think it did. That was a lot of words when you could have just did this. To each your own, but just for future reference, if there are calculations involved, don't explain to me how to do the math, because they're going to read it and say, I'm an intelligent adult. I don't need you to explain to me how you did it. Show me how you did it. And that's part of the coaching. That's part of you seeing how to approach these problems from a different perspective. And this is how I would rather you approach it, because it's a lot easier for me to see this than to read it and say, okay, they multiplied. Okay, I got you. So versus this, I know exactly what you did. Okay, so let's talk about the describe. So this is the part where hopefully you went back and you looked at your notes to be able to explain all of that. So the first thing we would do would be what? Mass out how much? You can write the words, that's fine. But K2CrO4 is a lot easier than potassium. To each their own, whatever, that's fine. So mass out, blah, 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 potassium dichromate. Okay, what are we going to do after that? I sure did. What goes on that blank? Very good. Now, do you agree that that would be a really, really large volumetric flask? Yeah, think about that. That's a really big flask. So a 7-liter volumetric flask. Okay? Then what would you do? To do what? Very good. Well done. And again, I'm using quotation marks. What's wrong? You okay? You sure? Okay, just making sure. So, we're going to mass out the starting compound. We're going to put it in a volumetric flask. We're going to add enough hot distilled water to practically dissolve the solid. Then what? That's the part that I'm hoping that you expanded to. There are minimum expectations, and then there are exceeding expectations. That last sentence that I put ... is exceeding expectations. It's restating the question and your answer. How often do y'all hear that? Exactly. Restate the problem. The problem was creating a solution, right? At the very end, we're going to restate what that solution is to prove that we know what our result would be. So to create what specifically? Okay. Now, I do want to ask you about that. Do you have to include this in the end? You don't have to. It might be helpful, but really, because you are in a volumetric of 7 liters, we know we're creating that much. So you're creating what concentration? Is it 0.75? 0.750 molar K2CrO4 solution. Yes, ma'am. I know it's not a sentence. I hit the period and I was like, I don't need that, and I just forgot to go back and erase it. But those ellipses were there to kind of make an emphatic point. Obviously, you would not include those. But yeah, just be one of them. Most definitely just one of them. Yeah. And we are going to try to do a solution dilution lab for sure. Yep. No, they will. It will be just like it read. It's implied math. I'll tell you this: if you realize that I've got to get their numbers into another form to get to my answer, it is implied that you must show that work. Okay? Alright, so let's move on to the next part. So 4, describe how you would prepare that same solution from This time, has it changed with what you're starting with? Yes. This time, you're starting with a 2.25 molar potassium dichromate stock solution. That one word was generous because it gave you a clue. What was that one word that gave you the clue? Stock. Had they left that out, I have a feeling that a lot of you would not have understood what to do here. Because what I'm trying to get you to see is, are you starting with a volume? Does that volume have a specific concentration? And you're creating it from. Do you agree that this is whatever that English term is? It's using to describe you're getting a result from something, and they give you a concentration. So, do you agree that you're going to have two flasks present? One is what you start with, and the other one is what you're going to end with. And you've got to realize, how do I get from the thing they're giving me to my result ending that they want? Then that stock is that key word. So this question is getting you to the point where you're understanding with what's going on. So what would you use here? Very good. You have to use MSVS equals DVD. Now, the good news is, because of that word stock, you now know which molarity is applied to the stock. However, what if that word had not been there, and you did recognize that this is what type of problem, first of all? It is a dilution problem. Very good. Number 4 is a dilution. How do you know it is a dilution problem? Very good. So you're starting with a higher concentration, and it is being reduced. Okay, it is being reduced. And so this is a dilution problem. This is your dilution formula. Now, do you have to use the S's and the V's? No, you could use 1s and 2s. What other version do we have of this that we'll see a lot later? A's and B's. But those aren't dilution problems. Those are, but that N-word. Neutralization problems. And there is a little bit of a difference of how you would apply that. So when we get into acid-base chemistry, you're going to see this again. And I'm not going to call it dilution. I'm going to call it neutralization. But do they work the exact same? Instead of using potassium dichromate in water, you're going to use an acid and a base. But they work the same way mathematically. So you're given a volume, and you're given a concentration, and you're giving a concentration. So one of our pieces are missing is our volume. But which volume is missing? Volume of the stock. Very good. So solving for VS, which is going to be MdVd over S. Now, you guys are smart enough to plug those numbers in. I'm just going to kind of blow through that real quick because I don't want to take the time to do it. But what should have been your volume of your stock? Very good. You can plug numbers in. I'm just going to skip through this. You should have already done this. 2.33 liters. Yes, ma'am. Yes, they do give you point for substitution. Yep. So you would earn the point for technically plugging those numbers in. You would have earned a point for that. Okay? No, you need to plug numbers in. You do need to plug numbers in, yeah. But really, pretend that the green are numbers. You could have gone from yellow to green with numbers. You don't have to show the blue. Does that make sense? You technically don't have to algebraically rearrange. They know where you started. You could actually even start with the blue if you wanted to. Okay? Now, I'm actually going to draw this, and then I want you to use your words to explain it. So I'm going to start with, you are going to have, so it was 2.233 liters, right? What is the stock concentration? 2 1/4? Do you agree that this is plausible for what I can start with? Okay? And then I'm going to start with an empty one. This is going to be my stock. This is going to be my dilute. You tell me, how big does that dilute thing need to be? You'll see in just a second. 7. You know I'm creating a 7-liter thing, correct? What should the resulting concentration then be? So I've got to figure out how to take 5 liters of a 0.225 molar stock and get it to 7 liters of a 0.75 molar. So I've got to reduce the 2.25 into 0.75. So Nick asked that same question. Why do I have 5 liters? How much am I going to put into here from my stock? Very good. So I'm trying to show you, do I have to have exactly 2.33 liters of the stock to begin? No, I just need enough to get 2.33 out. You don't even have, this is, it could have been 3, it could have been 8, it could have been 9. This is arbitrary. This number does not matter. But does it have to be above 2.33? Yes. So really, that was just to prove to you that what the amount you start with just must be greater than the amount that you need. Yes, ma'am. I would say pour carefully or carefully pour, whatever is proper English there. Okay. So, now that you've seen, we've taken exactly 2.33 of the stock solution out, 2.33 liters. Once I have this in here, what would I then do? So then we've got distilled H2O. Mathematically, could you subtract to determine how much you need? Sure, which would be, what, 5.7? Yeah, 4.67, sorry. You could say, and then place exactly 4.67 milliliters of water. But then you're leaving room for error. I would say, pour, carefully pour. Which one is it? Carefully pour or pour carefully? Doesn't matter. Who cares? This is in English. Either way works, but put it in there safely. Okay? You're going to put exactly 2.33 liters of stock, 2.25 molar solution into the 7-liter flask. Are y'all with me? Yes? No? And then once the stock is in there, what do? Add enough water to fill to the line, to the meniscus. So you could say, if you wanted to go real deep, you could say until the meniscus reaches the neck, the mark on the neck. No. That's, go ahead. It doesn't matter. So let's talk about this. We're creating a solution. Does the temperature of the solution matter? No. In the other one, we're dissolving a solid. Does the temperature of the water matter? Yes. So that's the difference. That is the difference. So however you would want to explain this, I'm trying to show you the picture image of it, and you can decipher how you're going to get the 2.33 liters out, get it into the 7-liter flask, and then fill it up with enough water. You could, but I would make sure that you kind of explain it somehow. You could. I've actually never seen it drawn. I don't know if they give you credit for it. That's actually a really good question. That is a question I do not know. Okay? All right, any other questions on that? Yeah, in chemistry, if there's ever been a picture, it explicitly says draw or represent. Here, it says describe. So you're kind of getting in some gray area. Yeah. All right, number 5 is a really good question. 5 is a really good question. A stock solution containing barium ions was prepared by dissolving 23 grams of pure barium metal in nitric acid. All right, so let's think about that. Barium metal is a very soft metal, and you take it and you put it in nitric acid and it will dissolve. So I want to draw pictures. And again, because I think pictures sometimes help. So, first of all, what is the aqueous stuff in our beaker? Okay, it's HNO3, right? Does it tell you how much or anything? Okay. So a stock solution containing barium-2 ions was prepared by dissolving 23 grams of pure barium metal in nitric acid and diluting to a final volume of 2 liters. So we know that the final volume of this thing is going to be exactly 2.0 liters, and we started with 23 grams of barium solid. Okay? So let's think. This gets dumped into this, correct? So I have 2 questions for you. My first question, nitric acid, strong or weak? Strong, right or wrong? This is a strong acid. What is the definition of strong of anything? 100% dissociation. So under this blue water line, what are the things floating around in here? H plus and NO3 minus. Now, obviously, water is in there too, right? Do we need to really show the water? No, that's unnecessary because we know this is an acid, and all acids are in what kind of solutions? Aqueous solutions, and aqueous means mixed with water. You don't have to worry about that. But the barium is going to drop in here. And go back and read that first line. It says, what happens to the barium solid? It dissolves into what? No. And I know these lines aren't level, but it doesn't matter. So we had this, right? And go back and read that first thing. When it was dropped in, what did the barium turn into? Barium ions. Does it not specifically say a stock solution containing barium ions was present? So is that what that solution looks like? Yes, this is the resulting solution. 2 liters of barium solution with nitric acid present. Do pictures kind of help dictate what's going on? Okay? All right. Calculate the concentration of barium ions in the stock solution. So let me ask you something. All of these turned into these. True or false? True. And it asked you to calculate the concentration of this stuff, right? Well, we know concentration is what? So I ask you, do you agree that we have to get both of those units? Can we get moles? From what? You've got 23 grams of barium, so let's start there. So I've got 23 grams of barium. How do I get it to moles? Very good. Divide by 137.33 grams. That gives me 1 mole, which gives me how many moles? 0.1 what? 1.7. Why just 1.7? 2 sig figs, okay? And that's moles of barium. So I've got moles. Is everybody with me so far? Now, but they didn't ask for moles. They asked for what specifically? Concentration. So if I go back to this picture, I now know that I'm working with 0.17? 1.7 moles with how much volume? 2 liters. It said to a volume of 2 liters. So what is the concentration of my stock solution? Moles divided by liters. 0.085. That is of the solution, right? Because it says dilute the final formula, calculate the concentration of barium ions in the stock solution. Okay, so what they're asking, they're not worried about the hydrogen and the nitrate. And the diluted solution. That's the next part. That's a totally separate part. And the diluted solution if the stock solution was diluted to 500 milliliters. So we've got to separate that. Okay. That is the concentration of the barium ions after you took all those pellets and dumped it in the acid. That is the stock solution. This is what we're starting with. Remember how I asked you how do you create that solution? You mass out blah, blah, blah grams of blah, blah, blah. I massed out 23 grams of barium. I dumped it in the acid, and that was the concentration of the solution after it dissolved all those pieces of barium. You with me? Sure. Okay. Now this is, yes, sir. I just gave you one of those answers. And you fussed about, could you do it on the test? No, because it has to be to the negative third power. This would be to the negative second power. Okay? Alright, so then it tells us, so we've calculated the concentration of the barium ions, and calculate the concentration of barium ions in the stock solution and in a diluted solution. So now we're going to dilute it. If the diluted solution, if the 125 milliliters of the stock solution was diluted to 500. So they've used the word stock and dilute. So what's our formula? Okay. All right. So we've got MSVS equals MDVD. Now notice what the question's asking you for. Calculate the concentration of the barium ions in the stock solution and where? In the diluted solution. So this question, what are we solving for? The molarity of the dilute. Are you with me? Okay, so we're going to go with MD, which is MSVS over VD. Okay, so calculate the concentration of the barium ions in the stock solution and the diluted solution. If the 125 milliliters of the stock solution, so have they just given us, yes, thank you, VS. So they've just given us VS, which is what? 125 milliliters. Okay. Was diluted to what? 500. Diluted to this volume. So what would that be? VD, the volume of the dilute, right? Which is 500 milliliters. Now, some of you are looking at this like, hold on, wait a minute, what's up? Go ahead. Okay, that's where I was going with you next. Do I have to be in liters here? Let's actually look at both versions and let's prove, because sometimes math is better to prove it to yourself if you do or if you don't. Okay, well, I don't want to tell you. I want you to prove it to yourself. So we know it could be 0.125 milliliters. Excuse me, liters. My bad. 5 liters divided by 0.500 liters. Now my next question, what's the only variable that I'm missing? MS, which is the molarity of the stock. Does it give you the molarity of the stock anywhere in this question? No, but have you solved for it? Yes. Which was what? So here's what I want you to do. I want from Sarah right and from Brianna left. Excuse me, Sarah right. Y'all do the top one. Just punch it in. And from Brianna left, do the bottom one. This way, y'all do the bottom. From here, y'all do the top. And I'm going to try to get you to prove whether you do or do not have to use milliliters or liters. And I want you to see. In fact, do it both if you want to really prove it to yourself. So, my top group, what did you guys get? My bottom group, what did you get? That's interesting. Our answer is the same. The answer of why it's the same is very easy. Why? Very good. Are these numbers the exact same? Yes. Are these numbers the exact same? Are you doing them? Are you mathematically changing them in the same way on both parts? You're dividing 0.125 divided by 0.5 and 125 divided by 500. The problem that you guys see is that 1.125 is way less than 125 and 0.5 is way less than 500. But mathematically, are they equivalent? So ratio-wise, would they result in the same ratio? Yes. So, and the simplest answer is, what do both units do? Leaving you with molarity. So since the ratio would be the same, the answer result will be the same. Does that make sense? So it does not matter what you use. You go what? You got it? You sure? Okay. So this is the molarity of the dilute. So that would be your concentration of the diluted solution after you, or if you only use 500 milliliters of it. Okay? Any questions? I think I gave you guys another one. I want to work 2 or 3 problems on it as well, just because it's a little different. We haven't done that one. Y'all seen number 1. I'm not going to worry about number 1 because. Say it again. Real quick, I do want to do one because it won't take long at all. Or number 2, excuse me. Commercial cold packs and hot packs are available for treating athletic injuries. Both types contains a pouch of water and dry chemical. When the pack is struck, the pouch of water breaks, dissolving the chemical, and the solution becomes either hot or cold. Many of these packs use magnesium sulfate. Many hot packs use magnesium sulfate. Many cold packs use ammonium nitrate. So before I ever go any farther, I'm going to tie this into a future problem. Samantha, do you need these sheets? They're up here. Both of them are up here. Hot packs. What does a hot pack mean? It gets hot. Which, Nick, it is what? It's exothermic. What do we know about exothermic reactions? They release energy. What is happening on the molecular levels with the bonds? This is the hardest part. When bonds are formed, energy is released. So, if energy is being released, what's happening to the bonds? They're forming. So when magnesium sulfate dissolves, is something else being formed to create the exothermic reaction? Yes. That is hard for students to grasp, because when we talk about this problem on the balanced equation level, what are you going to be seeing happening to magnesium sulfate? It's splitting. But this is an exothermic reaction, which tells me what else is occurring in this reaction. Other bonds are forming somewhere. That's the key piece of evidence. Now, the other one, where it says cold packs, what happens in cold packs? They get cold, which means it's a what? An endothermic reaction. Endothermic, what happens to energy? It's absorbed. Think about karate. How do you break a board? You put energy where? Into the board. So if you apply energy to a bond and break it, did the bond absorb the energy? Yes, which means that when ammonium nitrate is dissolved, more energy is required to break this thing than it gives off. But let me ask you, and this is what we're going to get in thermo. Why does it get cold? Very good. The surroundings are losing the energy. So if I sucked all of the energy out of you, what would happen to your body temperature? It would drop. So that's why things get cold. It's because the energy that is in the molecules around it has been absorbed. Whether it's coming from the glass, whether it's coming from the water, whether it's coming from the actual temperature in the surroundings. That's why it gets cold. And this is a thermochemistry concept that we're going to go really deep in. But I just want to show you this. So, write these reactions to show how these strong electrolytes. So let's pause there. What does strong mean? 100%, which means if I took that light bulb and I put that solution on that light bulb, what would it do? It would light up. Both reactions are going on. It just does. Icy hot's one of those weird, strange things we just don't talk about. It defies laws of chemistry. Okay, so strong electrolytes dissociate when they dissolve in water. So let's talk about magnesium sulfate. What is magnesium sulfate chemical formula? This is a minimum expectation. Okay, it's just MgSO4. Why are there no charges? Because they cancel. Very good. So this is going to turn into Mg2 plus what? SO4 2 minus. Now, and the way I would do it is I would say that this is delta H positive or negative. Exothermic reactions do what with energy? Release, which means what's happening to your total amount of energy? It's going down. Okay? And then you've got the other one, which, what is ammonium nitrate's formula? This is a good one. Very good. NH4NO3. What about it? You don't have to, but it's a teaching moment kind of thing. You do not have to do that, no. I mean, if you want to, you can, but you don't have to. It's proving your knowledge is really what it's doing. And this one would be what? Positive delta H, just because they tell us based on those things. All right, so we get on all that. Does that make sense? All right, so let's look at number 3. Calculate the molarity of each of these solutions. Okay, so you've got 5.623 grams of sodium bicarbonate, which is baking soda. What is another way to say this formula? No. Sodium hydrogen carbonate. Now, the reason it's bicarbonate is because of the -2 charge has been reduced by the hydrogen and blah, blah, blah. And dissolved in enough water to make 250 milliliters of solution. This is simple, okay? Peyton, you with me? What is the question specifically asking you to do? Okay, Peyton, what is the concentration? What does it stand for? Okay, moles over liters. I've got to get 2 units. Is one of them really easy to get? Which one's easy? The easy one to get. Okay, so 0.250 liters is really easy to get. Okay, the moles are a little bit more challenging because you got to find the molar mass, right? That is about as aggravating as it gets. I will tell you that trends in the past, they've actually started giving molar masses in the problems to help expedite the process, because they could care less if you can calculate molar mass. You should be able to do that, but can you know what to do when you have it? It's kind of the way they look at it. So 5.6, I'm not going to tell you they're going to do that on every problem, but we're seeing a trend of that occur. And I'm just going to write X because I don't feel like writing the whole compound. And what's the molar mass? Yep, thank you. 84.01 grams in 1 mole. And again, I'm just going to write this number right here, which gave us, okay, thank you, 0.669 moles. Is that again? Oh, my bad. Yep, there's a 0 in there. Which gives you a final concentration of 0.268. 0.2, actually, no. There's 4 sig figs. So 0.2677 molar. BS, baking soda.